For 1, we have midsegments. We know they're midsegments because they connect together midpoints of the big triangle. So if MN is 8, that means this is 16. So we have 8 and we have 8. If NL is 6, then that means the base for that midsegment is 12. So that's 6 and 6. And if ML is 5, that means its base is 10, the side it's not touching. So we have 5 and 5. We're asked to find the trapezoid, BM and C. So that would be 8 plus 5 plus 16 plus 6. And that is 35 when you add all of those together. For number 2, we're being asked which one does carry the rhombus onto itself, so which one does make it look like itself. A 180-degree rotation counterclockwise about the origin. So the origin is not in the center of the shape. So even though the orientation would be the same, it wouldn't make it look like itself because it's not in the point of rotation. The center of rotation is not in the center of the shape. So that one's not the correct answer. Let's check out the next one. Reflection over the line, y equals, that's supposed to be 1/2 x plus 1. So let's check that one out. Here's 1, the y-intercept of 1. The slope of 1 means up 1 over 2. So up 1 over 2, down 1, left 2. And that doesn't look like a line of symmetry to me. Remember, if we're reflecting over a line to bring something onto itself, it has to be a line of symmetry. Reflection over the line y equals 0. The line y equals 0 is the x-axis because along the x-axis, all the y coordinates are 0. So that is not a line of symmetry. And the line x equals 0 is the y-axis because along the y-axis, all of the x coordinates are 0. All of them go through the x coordinate of 0. And that is a line of symmetry. So that is the one that we're looking for, number 4. For number 3, it says which statement is not always true when we have a dilation by a scale factor of 3. So K is going to be equal to D because those two angles do correspond, and corresponding angles of similar triangles are congruent. Before and after a dilation, angles stay the same. KM is a third of DS. So that is true because DS is 3 times larger than KM, and those do correspond. So that's absolutely true. Let's check out with the area and the perimeter. What I like to do is I like to draw myself an example. So I'm going to just draw myself an example of 2 triangles, and I'll just make this 1, 2, 3, and I'll just make this 3, 6, 9. So it's a dilation by a scale factor of 3. So this will be triangle KLM, and this will be triangle DRS. So I'm going to actually just find, oh, I should have made them right triangles. That's easier. Let's backtrack because finding the area of non-right triangles could be tricky. So let me give myself an example with right triangles. I like to use 3, 4, 5. I know that that is a right triangle. It's a Pythagorean triple. So scale factor of 3, 12, 15. My original example would have been good with perimeter. But for area, it's easier with the right triangle. So let's check it out. Area of a right triangle is 1/2 base times height. So here, 1/2, 4 times 3, so that's half of 12, which is 6. And let's check out over here. The area is 1/2 of 9 times 12. 9 times 12 is 108, and half of 108 is 54. So, yeah, the areas are not 3 times. That is, let me do 54 divided by 6 on my calculator. That's 9 times. So that's not true. Let's check out the perimeters though. If I add all the sides, 5, 8, 12. So perimeter of one is 12. The perimeter of the other, let me add it on my calculator. 9 plus 15 plus 12, 36. Yeah, the perimeters are in that ratio. the areas are not. So 3 is the correct answer. For number 4, we need the exact value of BD, sorry, of the perimeter in simplest radical form. So this is a 90-degree angle because we do have a rectangle, so that leaves this one to be 60 because all angles of a triangle add to 180. So what we have here is a 30, 60, 90 triangle. So we have the biggest side. So what I'm going to do is get the smallest side. And then once we have the smallest side, we can get the middle biggest side. So since the largest side is 12, and we have the ratio 1 to radical 3 to 2, all I'm going to do is half that 12, and that will be 6, and that's going to be the smallest side. And then what we're going to do is multiply it by radical 3 to get the side across from the 60th degree angle, because from the smallest to the middle biggest, it's times radical 3. So for the perimeter, because rectangle opposite sides are congruent, we have 12 plus 12 radical 3, and that's our perimeter. Okay, moving down to number 5. For number 5, we're given that the length of diagonal AC is 12. This is a rhombus, so diagonals bisect each other. And not only do they bisect each other, but they are perpendicular to each other, making right triangles. So if this diagonal is 12, then each half is 6. We need the length of DB of the other diagonal. So if we find one piece of the diagonal, then we can multiply by 2 and get the other piece. So we can focus on any of these right triangles that we want. They're all the same. I'm going to use Pythagorean theorem because we have 2 sides of the right triangle. I'm just going to be really careful when I use Pythagorean theorem because I have the hypotenuse already. Across from the 90-degree angle is the 10. I'm going to make sure I plug in 10 for C. So I have 36 plus B squared equals 100. So now I just need to do 100 minus 36. And I got 64. So we have B is equal to 8. Okay. For the next one, we have a dilation centered at the origin. I'm going to take the original equation of the line, and I'm just going to solve for y. So I'm going to divide everything by 4. 7 over 4 doesn't divide evenly, so I'll just leave it as is. And it is centered at the origin. So we can just take the y-intercept and we can just multiply by whatever the scale factor is. But the thing that we have to keep in mind is that the slope stays the same before and after a dilation because dilations make parallel lines. So the slope will be the same. But I have to also see which one of these has the same slope as this one. So I'm going to just take all the answer choices and put them into y equals mx plus b form. So negative 4y for number 1 equals to negative 3x plus 9. Then I'm going to divide everything by negative 4. So this could be number 1 because it does have the same slope of 3 over 4. Let's check out number 2. For number 2, 4y equals negative 3x plus 9. And then divide everything by 4. Yeah, number 2 doesn't work because it has a slope of negative 3 over 4. Let's check out answer choice number 3. I'm going to move the 4x over and then divide by negative 3. But the problem is this is 4 over 3 and not 3 over 4, the slope, so that's not going to work. And then finally, the last one, let's check it out. And divide everything by 3. And already we see the slope is not the same as the original, so that's not it. Answer choice 1, our first one, is the only one that has the correct slope. Okay, we need a sequence of transformations that will map this quadrilateral onto this one. we do have a grid, so we do need to be using, like if we're saying rotation, degree measurements. If we're saying a translation, we need to be saying the number of units. If we're saying a reflection, we need to be saying which line we're reflecting over. I don't like to do rotations. I like to do reflections. So let's see if we can do this one by a double reflection. And then if we can't, we'll do a rotation. So I am going to reflect over the y-axis, and then I'm going to reflect over the x-axis, and I'm going to see what happens. So first reflecting over the y-axis, I'm going to 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. Oh, wait, I'm doing the wrong one. I need to make this one into this one. So I'm going to try doing over the x-axis, then over the y-axis. So let me try that one more time. 1, 2, 1, 2. And the only way to know is to try it out. 1, 2, 3, 4. 1, 2, 3, 4. And that's already on the x-axis, so that would stay. So that would be there. And now let's see what happens if we reflect it over the y-axis. So it's already on the y-axis, so it would just stay point D. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5. 1, oops. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. If I reflect it again, then maybe that would be the way I want it to be if I reflect it one more time. But this is getting too much. So maybe we just want to try to do a rotation here, because if you try to do a double reflection and it's not looking the way that you want to look, you might want to do a reflection. So the only way to know, and I wanted to show this, the only way to know is to try it. So I think it might be our best option to go with a rotation. So I'm going to reset that. But when I imagine trying to turn it, this one is really difficult to make match up. So I'm going to try one other thing. I'm going to try reflecting over the y-axis and then translating. So 1, 2, 3, 1, 2, 3. Because I need the orientation to match up. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And let's see if that makes the orientation the way that we need it to be. R matches up with R, A matches up with A, E matches up. Yes. Okay. So now we can just translate downwards. So, and to the right. So we need to translate, and I'll just go by D to D prime. So we need to translate 1 to the right, and 1, 2, 3, 4, 5. Oh no, 2 to the right. 1, 2. 1, 2, 3, 4, 5, 6, and 7 down. So reflection over the y-axis, followed by a translation to right, 7 down. For this one over here, the best way to do it is to redraw the 3 triangles. So in order to redraw the triangles, I'm going to just make sure the right angles are in the same spots. It doesn't matter how I put the original one. The medium one shares B, so I'm going to put those in the same spot, and then C is the one left over. The small one shares A, so I'm going to make sure those are in the same spot, and then C is what's left over. AC is 6. That's in 2 triangles. AD is 2. That's in just 1 triangle. And we are looking for AB, which is over here. So now I can make my proportion. 6 corresponds to 2. X corresponds to 6. So we have 36 is equal to 2x. So we have x is equal to 18. And x does represent the length of AB, so the length of AB is simply just 18. Over here, we need to prove that G is the midpoint of EF. In order for G to be the midpoint of EF, it would need to split it into 2 equal parts. So we need these 2 sides of these triangles. As soon as we need sides of triangles to be congruent, we should be thinking CCDC, which comes after proving triangles congruent. We do have these vertical angles over here. And remember, we can't use these. I'll erase these for now. That's what we want to get, but we don't know it right now. That's what we want to get with CCDC. We're also told in the givens that AB is parallel to CD and AB is congruent to CD. So the quadrilateral ABCD is a parallelogram. It has one pair of opposite sides, both congruent and parallel. So that means if it's a parallelogram, the other pair of opposite sides is parallel as well, creating congruent alternate interior angles. We do also have a diagonal of this parallelogram, and we know that diagonals of a parallelogram do bisect. Oops, sorry, we can't use that because we don't have 2 diagonals. So backtrack. We can't say diagonals bisect each other because we don't have 2 diagonals. EF is not a diagonal. It doesn't go from corner to corner. But I'm missing a given. The given I'm missing is that DE is congruent to BF. And since it's a parallelogram, not only is this pair of opposite sides parallel, but it's also congruent, right? AD is congruent to BC. So if I take AD and I subtract off DE, I get this side. And if I take BC and I subtract off BF, I get this. And then I'll have AAS to prove the triangle's congruent, and then I could CPCTC, EG, and GF. So I'm going to make my statement reason chart. And we have quadrilateral ABCD. We have AB congruent to CD. We have AB parallel to CD. And we have DE is congruent to BF. And that's all given. And from those givens, I know that quad ABCD is a parallelogram. If one pair of opposite sides is both congruent and parallel, it is a parallelogram. And from that, I know that AD is congruent to BC, so the other pair of opposite sides are congruent, and AD is parallel to BC. The other pair of opposite sides are also parallel. I should probably put these as 2 separate reasons, statements, I mean, because they do use 2 separate reasons. So I'll put that here. So for number 3, I'm going to put opposite sides of a parallelogram are congruent. And for this one, I'm going to put opposite sides of a parallelogram are parallel. So I'm going to do the subtraction first with the sides, and then I'll do the alternate interior angles. So let's start with the subtraction. So we're going to take AD. If we subtract off DE, then we are left with AE, which is what we need as part of this triangle. And on the other side, we're starting with BC. And if we subtract away BF, then we are left over with FC, which is the side of the triangle that we are interested in. So this step over here is subtraction. And then this step over here is substitution, because we're saying the result of the subtraction is this. The result of the subtraction is this. Now I'm going to put the alternate interior angles. So I'm going to put angle EAG congruent to angle GCF. And I'm going to put here alternate interior angles are congruent when parallel lines are cut by a transversal. And then I'll put the vertical angles. Angle AGE is congruent to angle FGC. And our reason for that is intersecting lines form congruent vertical angles. And then I'm going to continue over here. That's everything we need to say triangle AEG is congruent to triangle FGC. And that is due to angle side. And then we can use CPCTC to get EG congruent to GF. And from there, we can say G is the midpoint of EF because a midpoint splits a line segment into congruent parts. And that was a long one, but that's not for that proof. Not that bad, just long. So for this one over here, let's see what this one is. So for this one over here, we have EF is parallel to AD, and we have EF is parallel to BC. So we can see here that that means that AD and BC have to be parallel to each other. If this is parallel to this and this is parallel to this, then this has to be parallel to this. It's kind of like the transitive property. It's called the transitive property of parallelism. If this is parallel to this and this is parallel to this, well, then these have to be parallel to each other because they're both parallel to the same line as each other. So since AD is parallel to BC, and since it also says that AD is congruent to BC, we know that quadrilateral ABCD is a parallelogram because it has one pair of opposite sides that are both congruent and parallel. From the proof statement, we can see what triangles we're focusing on. We are focusing on these two triangles. And since we're proving a product, we do need to prove similarity. So we need AA. So we have the vertical angles. And since we have established that the quadrilateral is a parallelogram, opposite sides are parallel. So we have congruent alternate interior angles. From there, all you need to do is prove a proportion involving the corresponding sides. When you make your proportion, just make sure that you double check that when you cross multiply, it actually gives you the product that you want. So just double check. The reason for a proportion is the same every time. Corresponding sides of similar triangles are proportional. And then after that, you can prove your product, which is also the same reason every time. in a proportion, the product of the means equals the product of the extremes. Here is the full written up proof. So I first established that AD was parallel to BC, and that's due to the transitive property of parallelism. Then I said that the quadrilateral ABCD is a parallelogram because it has one pair of opposite sides, both congruent and parallel. And then from there, I could mention the alternate interior angles, the vertical angles, prove the triangle similar with AA, prove the proportion, and finally prove the product. Over here, we are told that BC is congruent to BH. Here's BC, here's BH. So what we have here is an isosceles triangle, which means the opposite angles are congruent. That's the base angle theorem. If a triangle has two equal sides, the angles opposite those sides are also equal to each other. We're told that the measure of angle, we're also told that these are parallel to each other, very important. So angle NCD is 62 degrees. What is PHK? So we're looking for right over here. So since we already know that the lines are parallel, we can use like alternate interior angles and corresponding angles. I see a vertical angle relationship right off the bat. Vertical angles are always congruent even if lines are not parallel. And that means this is 62. So we're doing well right over there. Since we do have parallel lines, I can use corresponding angles. So these two are corresponding angles. Backtrack for one moment. Okay, let's go back here and let's go back to the triangle. So inside of the triangle, a triangle always has 180 degrees. So 62 plus 62 is 124. 180 minus 124 is 56 degrees. So right over here, this angle at the top is 56 degrees. And I want to figure out what the relationship between this angle and one of the other ones that I have already is. What I'm going to do to actually make it clearer is I'm just going to highlight the parallel lines and the transversal close to the 56-degree angle, because now I can see that the corresponding angles actually are these two angles. So this one is 56 degrees. So when you do know that your lines are parallel, you do know that angle relationships like alternate interior angles and corresponding angles are true, that they're congruent. However, if you did not know the lines were parallel, you could not use those. You have to find those in order to prove the lines parallel. If you did not know the lines are parallel, all you could use are vertical angles. And the fact that supplementary angles make 180 degrees and that triangles add to 180 degrees as well. So you do need to fully explain your answer in words for this one. So I am going to write it out so that way you could see what that needs to look like. So I'm going to put that over here. Since BC is congruent to BH, angle BCH is equal to angle CHB, because if a triangle has two equal sides, the angles opposite those sides are congruent. Since the measure of angle NCD is 62 degrees and angle NCD is vertical to angle BCH, the measure of angle BCH is equal to the measure of angle BHC, and they're both equal to 62 degrees. Okay, since all three angles of a triangle sum to 180 degrees, 180 minus 62 plus 62 is 124 equals 56. So angle CBH is 56 degrees. Since angle CBH and angle, what is this, KHT, are, oh, PHK, are corresponding angles, they are congruent since lines are parallel. So measure of angle PHK is equal to the measure of angle CBH, and they're both equal to 56 degrees. And there we have a complete explanation. Yours doesn't have to be as thorough, but it does need to fully mention where everything came from. Okay, for this one over here, this is a blast from the past over here. We're going to construct an equilateral triangle that starts off with the hexagon construction. In order to do that, what I'm going to do is I'm going to put my compass here, and I'm going to extend here. Oh, actually, I'll just draw a radius. That's so much easier. And then when I draw the radius, I'll just measure it. Great. I'm going to come over here. I'm going to make a circle. Remember, this is the one with all the pretty circles. And then where it intersects the circle, the original circle, I shouldn't say the main circle, the original circle, we're going to make another one. And we're going to keep going around to all the intersection points. We're going to decorate it in circles. And we're going to end up with 6 circles surrounding the original one. So 7 in total, 6 surrounding the original circle. Got to keep going. And, oh, doesn't look like a pretty flower yet. Looks like it needs one more in order to be a pretty flower. There we go. Okay, so there we have it. Now, instead of connecting all 6 of the intersection points, since we are making a triangle, instead, I'm going to connect only 3. So I'm going to connect every other flower petal point. And there we have our equilateral triangle inscribed in the circle. For the next one, we are making a line that is perpendicular to AB. That's part 1, and then we're going to add on to it and make a parallel line. So let's start with the perpendicular line first. So what I'm going to do with the perpendicular line is I'm going to put my compass on point P. And what I'm going to do is I'm just going to make a circle. Oops. Be a little smaller. I just want to make a circle that intersects the line in 2 spots. So it doesn't matter like the distance that you use. We just want to intersect it in 2 spots. And then I'm going to go over to one of those intersection points. Oh, and we should probably open up to the distance between the 2 intersection points. Okay, so I'm on one of those intersection points and I'm swinging a circle. And then I'm going to go on the other of the 2 and just swing the same exact circle. And there we have it, right through those intersection points. I'm going to make my perpendicular line. I'm not 100% accurate on the computer. Try to be as best as possible. But as you can see here, it is perpendicular to the original line. So now the idea is in part B, when we're going to make a line parallel to the original line, is we're going to build on this construction. And what we're going to do is we're going to make another perpendicular line, but to this one. So it's perpendicular to this one so that these will be parallel. Because 2 lines perpendicular to the same line have to be parallel. So that's the idea of the construction. We're making a line that's parallel to the one that we just constructed. So what I'm going to do is I'm going to follow the same steps. I'm going to put my compass back on point P. And I'm going to do the same thing. I'm going to make a circle that intersects the line in 2 spots, but this time the line's not the black line. The line is the blue line that we just constructed. And it does get messy because it does get to be a lot of construction marks. Let me use a different color for the next arcs. I'll use yellow because I haven't used them before. So I'll just open up to the width of the intersection. That's what we usually like to do. And oops, I'm on one of the intersection points now. Oh no. And I'll just swing an arc. It's so hard on the computer to get this to swing. Give me one moment. There we go. Finally, it's swinging. Okay, now I'm going to go over to that other green intersection point as best as I can on the computer. I'm going to swing that same arc. And I'll use a different color line to connect between the two intersection points. And I'll make it a bit longer. Like, I'll just extend it. Okay. And as you can see here, it's perpendicular to the blue line, and it's parallel to the original. And that's it. It's just two perpendicular lines through the same point.